Okay, so this is a revision seminar for Intro Math Econ Basic in Semester 1 2014, for those who are listening on the video. And I've been asked to talk about differentiation, including partial differentiation. So let me make the focus. So I can't guarantee that I'll cover absolutely everything in your course because I'm doing it off the top of my head, but hopefully the things I say will be useful. So do remember you need to check a few things to make sure that I haven't missed anything when you're studying yourself. Okay, so what I'm going to do first is I'm just going to have a quick description of what differentiation is about, but not from the slopes of lines perspective, from a different perspective, so that you can join your partial differentiation stuff to your ordinary differentiation stuff, and it might help. And it might also help you to understand some of the things that will happen in your microeconomics eventually, so that you can, and possibly even macroeconomics, when you do derivatives in those, so that you can see something that will come up again later. So that's what I'm going to do. Okay, so differentiation is an action that you perform on a function to produce some new formula. So we have to start with functions. So functions first. So the idea in maths of a function is it's like a rule where you take numbers, or anything, doesn't have to be numbers, but you take numbers and you perform some sort of action upon them and you produce an outcome. And you can put as many numbers in as you want, and you'll only get one outcome out for each combination of inputs. So that's the idea of a function. So we have some number of input number 1, input number 2, input number 3, and they go in until you have some sort of process and it spits out an output. That's the general idea of a function. There's this really formal mathematical definition, but this one is easier to understand and just makes more sense. And so it doesn't matter how many, each function has a certain number of inputs and one output. And the idea is that for every combination of inputs, you always get the same output. So you're not allowed to say put in the numbers 5, 7, and 8 and get 4 the first time, and then put in 5, 7, and 8 and get a 6 next time. It always comes to the same answer. Okay, so basically the idea is that there's usually some sort of formula. Okay, that process there is usually some sort of formula. So your classic examples are something like this. You know, they're usually called f for function. Sometimes we call them g or h or pi, depending on what we want them to stand for. And you'll have, usually the inputs are called like x and y. And then there's some sort of formula that tells you how to get the outcome, the output. Okay, that's a stupid one that I just made up off the top of my head. But the idea is that I take these three inputs, x, y, and z, I do this formula and it produces an output. So in terms of my picture, I've got my input x, my input y, my input z. And I put them all into my function, which is called f, and it spits out this output. The idea is you figure out what this number is, and then that's the output. So as an example, f of 1, 0, 3 would mean that my x is 1, my y is 0, my z is 3, and I put them all into the formula, and I get 1 squared times 0 plus 3 minus 3 times 1, because the y was 0, so the x was 1, so 1 squared, the y was 0, so 0, the z was 3, and the 3 is still a 3, and the x is a 1, and I figure all that out, and it comes out to, ooh, 0, okay, didn't expect that. And so in terms of my picture, it's like I've got the number 1, the number 0, the number 3, they've gone into my function, and it's spat out the answer 0, okay? So the concept is that this formula isn't really it's not anything other than just a way of figuring out what this number that comes out ought to be. Okay? You don't need this picture, and I'm sure that your lecturer, when marking your exam, would be highly confused if you drew this picture on your exam, but the idea is that that's what a function is. Okay? And if I switched around the order of these, it would produce a different answer, because I have to know which one goes into which spot in the machine. Right. That's functions. Your classic functions only have one input and one output. I should say, look at this. This symbol here, F103, all of that represents today the number 0. Okay, so this notation here is the name of a number. It's the name of this number that comes out when I put 0, 1, 0, and 3. So when we talk about putting the F next to those brackets, we're saying that we take the numbers 1, 0, and 3, we perform the action F upon it, and the outcome is 0. That's what it means. Okay. Oops. I should number these pages so that I don't lose them later. So your classic examples of functions only take one input. Might be an x, might be y, might be a t. It's often a p or a q in economics. And they produce one output. So that one, for example, if I put the number 1 in, then I get out 1 squared, which is 1. If I put the number 0 in, I get out 0 squared, which is 0. If I put the number 2 in, I get out 2 squared. I should really do that properly. Which is 4. And I get any number I put in, I could figure out a number to come out. That's the idea of a function. And so I could, if I wanted to, make this big table, but technically I can also put in 1.5 and 1.57 and 1.57032118. Any number technically can go into that, and it's just that I've picked a couple of plain ordinary whole numbers, but I can put in any number I like into the function. And the numbers that you're allowed to put in I call the domain. Okay, so the concept here is that this number here is called f of 1, and this number here is called f of 0, and this number here is called f of 4. Okay, so this is saying that f of 1 is 1, f acted upon 0 is 0, f acted upon 2 is 4. Just to point out that I'm allowed to put in more than, it doesn't matter that doesn't matter if the same inputs produce, the different inputs produce the same output. It's okay to put in both two different numbers and get the same output. That's okay. As long as every time you put in a number, it gives you the same answer for that particular number, it's okay. Okay. That's the basic idea of function. And you spend a lot of time in most maths courses talking about functions of one variable. So this thing here is called a variable. Okay, so functions of one variable, they're really common, and we can draw graphs of them, but I'm just going to skip that bit till later and talk about something in particular at the moment. So I'm going to draw a picture of this function. These are my x's that I'm going to put in. I'm going to draw this lovely number line. I might put them a bit closer together if you don't mind. Okay, so here I have a number line. These are all the x's that I'm allowed to put into my function, and each of those x's will produce an answer. Okay? So I'm going to draw another number line where I'm going to draw all my answers. So, well, first, give me a second. This is quite a new approach to this. So each of those numbers produces an answer, right? So one picture of my function, so a picture. One picture of my function would be that I could draw for each of these what number it comes out to be. So if I put this into the function, the number that comes out is 0. If I put this into the function, the number that comes out is 1. If I put this into the function, the number that comes out is 4. If I put this into the function, the number that comes out is 9, 16. This one will be 1 as well. This one will be 4. And I could technically, for any number on the line, for example, here at 1.5, I could figure out that that actually came out to 2.25, yes. Okay, so any number in here I could figure out what it came out to. So this is just a picture of you know, it's almost as if for every number there's this arrow attached to it that tells me what the answer comes out to be. So I had this number line, and hidden under each of those numbers, like an chocolate advent calendar where you open the window, and underneath there is the answer. Okay, so that's one picture of a function. Okay, another picture of a function is a... No, I won't do that one. Another picture of a function is to take your x's that you're allowed to put in, okay, and draw a new number line of where those numbers end up, on where the answers are afterwards. So these are my outcomes. And I'll draw a new number line. I'm just going to need a bit more space so that you can see what's going on. Okay. Just need a darker pencil. This blue will do. So if I take this number 0, the thing that comes out when I do that is this number 0. If I take this number 1, the thing that comes out when I put it through the function is this number 1. If I take this number -1, the thing that comes out when I do the function is also -1. If I put this number 2, the thing that comes out when I do that function is 4. Okay, so I can have this before and after picture. Whereas I took this number 1.5, it comes out to here to 2.25. So the concept is that if I took the entire of that real line, I'll just colour that in a slightly different colour. If I took all of these numbers and I put them into the function and drew the dot that they all produced, what I would produce is this. I wouldn't be able to produce any of these numbers because it only produces positive answers. So the idea is that this is a picture of the domain, and this blue line here is a picture of the range. These are all the numbers that come out. Okay. This is the picture I want to focus on to help you make a connection between ordinary derivatives and partial derivatives. Okay, so I could have labelled my points as like A, B, C, D, and E, and then this one's A. No, this one's where B goes. This is where both A and C go. This is where D went, and this is where E went. So you can see where it is before and after. I don't have to do that, but I just want you to realise that there's more than one way of drawing a function. Okay, so the final one, just so that you can see it. This picture is called the graph. And the idea is that you put your x here, the same as we did before. And instead of just writing down what the number is, we go that distance upwards or downwards if it's negative, and we put a point, a dot in that spot. So the concept is that this one would go, the answer for this is 0, so I will go up 0 and put a dot there. The answer for this is 1, so I'll go up 1 and put a dot there. The answer for this was 4, I'll go up 4 and put a dot there. The answer for this was 9, I'll go up 9 and put a dot there. And the answer for this was 1, the answer for this was 4, the answer for this was 9. Okay, and I could draw dots to represent where all of the points end up in this picture here. So I can draw a height for each of those points, or a depth. If it was negative, I'd go downwards. This is called the graph, but technically I'm supposed to do it for every possible one, so I'd get 2, and if I put in 1.5, it would end up with 2.25, which would be there, and then I could fill in all of those dots and eventually get this nice smooth line. So just need to point out that those dots actually are not special. I just happen to pick them. I have to know for all of those, every possible point on the x-axis, I have to be able to figure out what height it ends up at and to connect all those points together as a single line, and that makes my graph. So all of this is the line, not just the dots. Okay, so for every point here there's one, well I haven't drawn it, but it's there on the line. Okay, and what you normally do is you stick in a y-axis, like that. Something like that. They're all supposed to be evenly spaced. And so what this is called, y equals f of x, or if you like, y equals x squared. So that's the idea of a graph. And what this means is that algebra is connected to geometry. Okay, so what we've managed to do is by simply drawing what that function, the heights that belong to all of those x's, we've managed to create this awesome curve, which is a parabola, and that means that it should work the other way around. If I have some sort of curve, it should be possible to find a formula that this would be the graph of something. Okay? Right. I'm going to focus on this to talk about derivatives, this picture just here. Let me just mark my pages. Okay. Okay. So the concept of derivatives or differentiation is to try and figure out how the output changes from that function when the input changes. Okay, so we want to know if the input changes by a little bit, how will the output change? Okay, that's the question that derivatives are answering. Just let me put the focus on a bit better. So if the input changes by a bit, how will the output change? Okay, that's the question that derivatives are answering. And it's answering it even better than that. You know how all of those points on that graph I drew had to be filled in with really finely grained differences in x? I want to know if I have a really finely grained difference in x, how will that affect the finely grained differences in y, in the output, which we normally call y, because it comes after x. Okay, so just as a concept, you've got your function and it's got all of these things that go into it, possibly only one. And we're saying, well, what if we change this x by just a little bit, and I make it go a little bit bigger? What will happen to the output? Will it get a little bit bigger? Will it get a little bit smaller? Will it get a lot bigger or a lot smaller? How is that output going to change when I change the x a little bit? Okay, so you could, if you wanted to, try and figure out what happens. You could stick in x equals, like I had on the first page, x equals 1, y equals 0, z equals 3, and that comes out to 0 for our particular function. And then you could stick in x equals 1.003, and say, I'm going to change it by a teensy bit and see what happens to the output. And the whole idea of differentiation is so that you don't have to do that every time. You don't have to test a whole lot of different changes in order to figure out what will happen. Okay. So in science, a change in x is represented by delta x. And when we have a really, really, really tiny change in x that's so small that it might as well be almost 0, then we represent it as a dx. Okay, so that delta is the Greek letter from which the Romans stole the letter D when we first had it, when the Romans first made the alphabet that we use in English. And so that's why we use a D, because the delta is a D, it's a capital D, and the D is also a D. So that's why we use the same letter there. Okay, and what these are called, these things here are also known as differentials. Okay. Right. So what we want to know is if we make a tiny change in x, what happens to the matching tiny change in the output. Okay, so this is the concept. So, what I want is a formula that says that, so what we want is a formula that goes, a change in f will be approximately equal to some calculation based on the change in x. Okay? That's the idea that we want to get around it. Okay? So that's an approximately equal to sign there. So it's saying if we know how much x changes, we should be able to do some sort of calculation and figure out how much f, the outcome, changes. Okay? That's what we want a formula for. And what we want it to do is want it to be, if we use really, really tiny changes, it'll be so accurate it'll actually be equal. And so we want this sort of df okay, so it will actually be equal to. That's what we want, okay? Right, and it might be that that calculation will have to be based on dx and dy and dz, okay? So that's what we're looking for. We're wanting some sort of calculation based on those things. Okay. Just let me pause for a minute and just have a quick look at something in your notes. Yep. Okay, so let me go back to this original picture, the one with the blue. I'll do it for just an ordinary function here. Okay, so suppose I'm here, I have to know where I am. Suppose I'm here at 2. And I make a very small change in x, like that. I know that the matching outcome for 2 is 4. So I want to know, if I move a little bit here, what will happen to the matching point? So this matching point just here, where does it go? Okay, so it has to go somewhere. And I want to know, if I change this dx, what's going to happen? How much is this going to be? That's my df. That's what I want to know. And I want a formula that tells me how big this is relative to that. Okay? And so if you want to know how big something is relative to something else, what you should do is you should do a division. So if I have 20 things and you have 10 things, and I want to say, well, how big is mine relative to yours? I say, well, I've got twice as many. That's the idea behind it. Okay? So I want a formula that says something along the lines of df compared to dx is going to be some sort of formula. Okay? So I'm thinking that I don't just want a calculation based on dx, I want something times dx. That's what I really want. Okay? So what I'm actually going to do is I'm actually going to want, in this case, df on dx is going to be 2 lots of dx that I'm currently up to. Okay? That's going to be my calculation. Okay, so the concept is that df is going to be 2x lots of dx. This is my calculation based on dx, and it tells me how much df is. So I know that if I'm at 2, then I'll chuck the 2 into that formula there for the x, and that'll give me 2 times 2. And then if I want to change it by, say, 0.1, I can put 0.1 into the dx, and then that'll tell me how much the df is. It'll tell me how much the f changes. I'm just going to do another example. So just as an example, this was my example. What if f of x was 3x plus 1, say? Okay, so the concept is I have to be at a particular point. Let's pick this point here. Doesn't have to be 2, it could be any point. And I do a calculation to figure out where that goes. So if I put 2 into the formula, I'll get 3 times 2 plus 1, which is 7. So this one goes here. And I want to know if I change the x by a little bit, what will happen when I change the y? So I know that if I change the x by 1, right, if I go from 2 to 3, then this will go from, if I put 3 into the formula, I'll get 3 times 3 plus 1, which is 10. And so this one will end up there at 10. And so my change in f will be 3 times the change in x. Okay, so I can do that change there, 3 times the change in x. And even if I make a really tiny change, the change in f will still be 3 times. Okay, so this will be 3 times as long as the change in x. So the concept is that I've got that df will always be 3 lots of dx, or if you like, df on dx is 3. This is the idea of a derivative. It's a formula that says how big the change in f is, or whatever f is, corresponding to the change in x. Right. One more. And then I'll just get on to the nitty-gritty of just calculating stuff. I just wanted to have a nice explanation that I could direct people to in the future. Well, that was page 5, wasn't it? I'll have a function of 2 variables this time. f of x, y is x times y. So this time I've got an x here and a y here, and together they produce this outcome. So if I'm here for x and here for y, together those 2 numbers in the formula produce whatever they produce. Okay, together they produce an answer. And I want to know if I change x by a little bit, or I change y by a little bit, or possibly both, what will happen to f? So if I change x by a little bit, like that, well, f might change by a little bit as well. And it might be big, it might be small. And if I change y by a little bit, then there'll be a matching change in f as well. And together, those changes are my df. So the idea is that any change in f is going to be caused simultaneously by a change in x and a change in y. So if the y doesn't change, then the orange bit isn't going to be part of the formula. Okay? So that's the idea behind it. Okay, so we use curly D's to point out that there's actually supposed to be 2 changes simultaneously here, one in the x and one in the y. So I'll just write this first. df is going to be something times dx, which is this blue bit, plus something else times dy. The change in x is going to cause a matching change in df. The change in y is going to cause a matching change in f as well. And we'll just add the 2 changes together because they'll add up to change f by whatever they change f by. Okay, that's the idea behind it. And the name for this, the name for that formula there is called df on dx with the curly d's. And the name for this formula is called df on dy. Okay, so that's the name of what goes there. In the same way that if I have df on dx, df is something times dx, the name of the something is df on dx. This is where it gets quite confusing because this looks like a fraction, but it's the name of whatever formula goes in that spot. All right, I don't know if that helps, but it certainly helps me, so I thought I would at least tell you that. And so derivatives in multi-dimensional calculus, where you've got functions of multiple variables, are not all that different from ordinary variables. It's just that each variable separately has its own effect on the outcome. And so you have to add all those effects together when you do any derivatives. Okay, this is called a total differential here. And in your notes, I think it's called like the small change formula, something like that. I think I just saw it as I was going past. Small increments formula. Okay. Right. Which is all well and good, right? But the idea is that we shouldn't have to go through this whole process of drawing pictures and calculating stuff to try and figure out what the formula is that goes in this spot that tells me how df is related to dx. Okay, so therefore we have all these rules. So the rules for differentiation cover all the famous functions that we're used to, and they tell you how to figure out what that formula is that goes in that spot. And there's also this other notation you can use. Actually, can I just skip that? I just want to say, before I get to that, okay. There's this idea, right, that derivatives don't just tell you how the outcome changes when you change the inputs. They also tell you something that you can do to a function. So you can take a formula, you can perform this crazy process and create a new formula. Okay? So instead of having your original function which tells you, you've got your original function which has an input and produces an output. And instead of it just telling you what happens when you change x by a little bit and then change y by a little bit, what you can do is you can say, well, what I want is a formula that if I chuck in x, what it will tell me is what dy and dx is at that particular x. Okay, and the name of this function is called f dashed. That's the other notation. Okay, so f dashed is a new formula that tells you at every particular x what the relative change between y and x actually are. Okay, so it'll tell you that dy equals something dx, and the f dashed tells you what that something is. So the idea is that we know that dy is sort of something dx. One of the names for this function is f dashed x. Okay, so the idea, or prime, or whatever you want to call it, most people call it dash, even though it's an apostrophe. It's just a name for a new formula. So this is like, okay, it's a new formula. So I just thought I should point that out. That's called the first derivative, and if you just want to do the derivative again, then you could do a new formula where you can just take that formula and treat it as a brand new function and find the derivative of that. And when you're doing it in multi-dimensions, if you had an x and a y, and they produce a z, then you know that if you had dz is something dx plus something dy, this is also called f with a little x like that, and this is also called f with a little y like that. So it says if I have a particular x and y, I can sub them in and figure out how quickly that z is changing when x changes at that spot. Okay, I should just point out that notation. And so you'll find that those two notations are mixed together. Sometimes you'll see a dy on dx, sometimes you'll see an f dash, sometimes you'll see a curly d on curly dy on curly dx, and sometimes you'll see an f sub x. And you need to be able to know that they mean the same thing in terms of what they're achieving. But the subtle difference is that this is more about trying to find a new formula, whereas this is more about trying to find the current change in y relative to the change in x. But they're not really different, and they're treated the same. Okay. back to my rules for differentiation. So there's classic functions that you should be familiar with, and you should know what their derivatives are. And there's a list of them on the Maths Learning Centre webpage, and I'll put them up on your page and when I email it out to you. But I'm just going to go through the list at the moment. So if this is f of x, then this is f dashed of x. Okay, so the concept is that if f of x is a constant, so when we go back to this machine here, it always produces the same answer. No matter what you put in, it always produces the same answer, and that answer is c. Which means that if x changes, then y doesn't change at all. It's always the same, no matter what. So therefore, the derivative is always 0. Okay? If you put in just x, then the derivative is 1. Okay, so if when you put x in, the answer that comes out is also x, then if you change x by a little bit, then the outcome is x, so you'll change it by the same amount. And so dx on dx should be 1, because they should cancel each other out. If you see anything that's like a constant times x, the derivative will be whatever that constant is. They're the real fundamentals, those three. They're the fundamental rules of derivatives, that the derivative of constant is 0, the derivative of x is 1, and the derivative of constant times x is just the constant. And then there's these rules which go, if you have x to a power, where n is anything, it's allowed to be any number at all, positive or negative, then the derivative is you multiply by the current power, and then you reduce the power by 1. So this is multiplied by current power, and then add a minus 1 to the power. That's our classic power rule. All right. And then there's some specialised functions that are really useful to know. That works for any powers. So that works for half powers, so you can do roots. And then there's some specialised functions. So e to the x, its derivative is e to the x. Other than 0, it's the only function that when you differentiate it, the function you produce is the same as what you put in. Just going to check that I'm covering the whole list. ln of x. So ln is the opposite of e. It's the e to the power of. If it cancels out an e to the power of if you use solving equations. If you differentiate that, you'll get 1 on x. Yep. They're your classics. And for your own purposes, it would be good for, it would be really good for you to put a list like this, probably much smaller, on your cheat sheet, if you get one. You get a cheat sheet, don't you? A list like this, but much smaller. And for your own purposes, it might be useful to stick a couple of them that are still technically on this list already, but remind you of some stuff that will happen. So just some special cases would be, x root x. Well, that's the same as x to the half, because I can convert it to a power, and then once I convert it to a power, I will multiply by the current power, and I'll add minus 1 to the power. So a half minus 1 is minus a half. So just as a check for yourself, it might be good to put a couple of them on there that you find that you have trouble remembering what to do. Okay, so most things can be interpreted as powers. If you put a 1 on x in this side here, the rule is that you rewrite that as a power. 1 on x is the same as x to the power of minus 1. And then you can go multiply by current power, and it'll be x to the power of, and then we'll reduce the power by 1. So minus 1 minus another 1 will be minus 2. So if you want to, you can rewrite this as a half times 1 over root x. And this one would be minus 1, whoops, not a times, equals. This one would be minus 1 over x squared. Because x to the minus 2 is the same as 1 over x squared. So there are a couple of the classics that are used really often in this sort of setting that it's useful to have as a separate list, so to remind yourself how they work. Okay, I might add a couple of the things to the bottom of this list a little later after I've talked about a couple of things. So there's those basic functions, and then there's this concept that you can, if you combine functions in a certain way, you can produce new derivatives by doing various of the rules. So there's these rules that tell you what you can do to figure out new derivatives. So, okay, so the first two are usually called something in your notes, but I like to call them by my own names because I can't remember what their real names are. They're not, you don't need to number them or anything, but I'm going to because I need to have something on my notes, and they're probably numbered differently in your notes. So rule number 1 is that if they're added or subtracted, then you can do each term separately. Okay, so okay, you can do each term separately. So that would mean if I saw that, I could just go, well, the plus creates these two terms. This is the first term, this is the second term, and I can just do each term separately. That one I will times by the current power, and the power will go down by 1. In fact, that's a worthy one of sticking in your notes directly. X squared. The power will come down, and it will be x to the power of 1, but x to the power of 1 is the same as x. Okay. And this one, times by the current power, make the power go down by 1, and that's what I get. I can just do each bit separately, and even if there were minuses between them, it wouldn't matter, I could just keep the minus there. Okay, that's rule number 1. Rule number 2 says that if it's currently multiplied by a constant, then that constant will still be there after you differentiate. So if you multiply by a constant, then that constant will still be multiplied afterwards. Okay, so you might be something like that. It goes for dividing by a constant as well. That works too, multiplying or dividing by a constant. No, I won't do that. Yes, I will. Something like that. So I know from rule number 1 that I can do each term separately. So this one says, look, the 2 has been multiplied on, so because it's been multiplied on, it will still be there after I differentiate. It will still have a 2 times. And then I can differentiate this as I normally do. Times by the current power, reduce the power by 1. This one is really 2 times 1 over x. Okay, so I can imagine that my 2 over x is really 2 times 1 over x. And the derivative of 1 over x, I really should have rewritten this first. Okay, so that x to the minus 1 will give me times by current power, reduce power by 1. And this last one, the divided by 5, will still be there because it's technically times by a fifth, and it'll be 3x squared. So I'm going to get 6x squared minus 2x squared. plus 3x squared on 5. I mean, technically I probably should have combined them together into a single number to begin with, but it doesn't matter. So if you were doing this in your exam, you would normally combine this 6 and this 3/5 together into one number. But I'm just going to leave it as it is for the moment. I don't think anyone will really care. And note that that -2 times that -1 became a +2. Okay, so you'll find that that multiplied by constant works really well. Just as another example, f of x is 3e to the x, then f dashed x. The 3 is multiplied on, so it'll still be there afterwards, multiplied on. I'll put a +2 there. The derivative of e to the x is still e to the x. That's all fine. And then I'll do the derivative of the 2, and so it will disappear. Okay? So just to point out that constants that are multiplied on will still be there afterwards. Constants that are added on will disappear when you differentiate them. Rule 3, I'm going to do the chain rule now, which is not normally done at this stage, but I'm going to call this the chain rule. I'm going to do it now. The chain rule is really cool. It allows you to put functions inside other functions. And there are many ways of writing it, and they are all fairly difficult to understand, but just want to point out that there are lots of ways of writing the chain rule, and in practice when people use it they don't normally tell you that they're using the chain rule at all. So it's worth noting that. So there are two ways of writing it. If you see something like that, then the derivative that's one way of writing it. So this says we differentiate the outside as if it was just an x, and then instead of x we put the entire formula for g of x in, and we also have to multiply by whatever we get when we differentiate g of x. And the other way of writing it is to say that dy on d, say t, is the same as dy on dx times dx on dt, something like that. It's your classic chain rule. It's two ways of writing it. They mean the same thing. In fact, just to be even better, I might do it as dy on dx is dy on du on dx. Okay, so this bit here is called dy on du, because what we do is we call the g of x, we call that entire thing u. And then this bit here is du on dx, because g is renamed as u. So if you really want to make it nice, you can actually go a g there if you like, because it's a little easier to see what's going on. That's the chain rule. So I just want to draw a picture to show you how the chain rule works. That's my x. That's my g that comes out when I do g of x. And that's my f. This is my picture. So the concept is that I pick my particular x, and it goes to wherever it goes when it produces a g. Okay, so I put my x into the function g. So if we're going to actually draw it as pictures, actually, let me change this. This is u, and this is y, and this process here is g. So I do g, and it produces u as my answer, and then I do f on the answer, and it produces y. Okay? That's my idea. I'm going to join these machines together, and I'm going to use the output from one machine as the input for the next one. Okay. And then I'm going to put that answer into the next function, and it'll produce whatever it produces. This is y. So, and this process is f. Okay, so my actual idea is to ignore what happens in the center. Okay, I want to go direct from here to there in one go, from x to y. And so I want to know when I do this little change in x, how big a change in y does it produce? Okay, that's what I want to know directly. But it's a little easier to go, well, what if I knew instead how big the change in x was relative to the change in g? Sorry, u. And what if I also knew how big this was relative to that? So what if I had from the first step that du was something times dx, and then from the next step I had that dy was something times du, that's this bit here. So what I can do is I can sub this in there, and I can go that dy is the first, I'll put 2 question marks there. The first question mark is actually this, but all of that is du, like that. That's my picture. This is all just pictures, it's not really a proof. But the name for this, the name for that question mark is dy on dx. And the name for this double question mark is dy on du. And so what I've got is when I divide by dx here, I've got dy on dx is that times that, and this one was dy on du, and this one was du on dx. That's the idea behind the chain rule. This working here is irrelevant, really. The idea is that dx causes du to change, and the du causes dy to change. And because it's all about multiplication, if this is twice as big as that, and this is 3 times as big as that, then what you're going to get is that this will have to be 6 times as big as that. Okay, so if this causes that to times by 2, and this causes that to times by 3 like that, together it'll be times by 6. So you have to multiply those 2 rates of change together to figure out the overall result. So that's a picture of it. If that helps you go, that's awesome. If it doesn't help you, completely ignore it and do something else entirely. And this is just a way of understanding it. The reason why I do that is that picture helps me when I do partial derivatives, the chain rule with partial derivatives, which you haven't learned. But I have to do it with the Maths 1Bs and with the intermediate Math Econ 2. They do chain rule with partial derivatives. So I like to have something that sets up for later. Okay, so the way that the chain rule works is that most people don't do it when they don't actually explicitly write any of those things. They just do it in one go. And your classic example is this one. That. So the concept is that we pretend it's an x, okay? And if it was an x, the derivative of e to the x would just be e to the x again. Okay, that's what would happen if it was an x. Only it's not an x, it's actually a 5x. And so because of the chain rule, I'll have to multiply by the derivative of that, which is 5. And that's your classic chain rule with e to the whatevers. How about another one? Something like that. ln of 2x squared plus 1. So what I'm going to do is I'm going to imagine that, I can imagine those 2 lines, and I can figure out how the ln changes when the inside changes. So I'm going to cover that out and pretend it's just an x. If that was just an x, the derivative of ln x would be 1 over x. So it would be 1 over x. Only it's not an x, it's a 2x squared plus 1. So I'm going to have to multiply by the derivative of what's here. And the derivative of that would be, well, let's see, the 2 is multiplied on, so it will still be there. And the derivative of x squared would be 2x. And the derivative of 1 would be 0, so I get that. And so I do a little bit of algebra to make it look prettier. something like that. It's a crazy, stupid function. We're just going to run with that. Okay, well, I know that the only way for me to figure out that derivative is to rewrite it as a half. Okay, so remember that if you are figuring out derivatives and you have to do a calculation before you do the derivative, leave space for it. Don't just go equals, 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 equals. The moment when it becomes a derivative, you need to put the answer, the f dashed or the dy and dx in. So if that was an x, then I would have x to the half, and my derivative would be a half of x to the minus a half. Only it's not an x, it's an x plus 3x squared. And so I have to multiply by the derivative of what's on the inside. So the derivative of the x is 1, the 3 will still be there, and then the derivative of x squared is 2x. So it's tradition to put the powers at the end. It's not necessary, but normally you'll put the 1 plus 6x, which I just made here, and then you'll put the next one. And that's a perfectly acceptable answer. It's actually okay not to rewrite that as things with fractions and roots. That's okay. And it's actually okay to have left it like this. It's just that most people who deal with algebra feel better having the powers at the end and the things without powers at the front. So that's just how they traditionally write it, and so it would be easier to match whatever the mark scheme said if you rewrote it this way. So you have the lower powers, well, the things without powers at the front and the things with powers at the end. That's the chain rule. It's actually the most important rule. It's much more important than any of the other rules. Okay? And then there will be another rule. What page was that? Okay, so there are two more rules which are really useful, and there is the product rule and the quotient rule. So product, of course, means multiplication. So the product rule is used in situations where you have two things multiplied by each other. So it says that you actually have to do two separate calculations and add them together. So this is what the rule looks like with the f dash notation. Yeah, whatever. If you have something that's two things multiplied together, then when you do the derivative of the whole thing, you'll differentiate one of them and keep the other, and then separately figure out, keep the other, one of them and differentiate the other. So this one, the g is differentiated, this one, the h is differentiated. It doesn't matter which one you differentiate first, as long as in one of them you would differentiate one and in the other part you differentiate the other, and you have to add them together. The reason this works is because of partial differentiation with two variables. So back here, when we looked at this, that plus in the product rule comes from here. That's where it comes from. Because what we're actually doing is we're treating this as a function of two separate things. F is a function of g and of h simultaneously. And so we actually have to do the partial derivative of f with respect to g and the partial derivative of f with respect to h. And that's how it all comes out. I'll show you that with partial derivatives in a minute. No, I won't. But that's where it comes from. That's why the plus is there. So one of the things I find really useful is showing this so that you can remember that there's a plus in this thing, and there's also a plus in the product rule. Okay. So it's designed for things where it's too hard to, say, expand the brackets. So lots of things you can expand the brackets, but some things just don't help. And your classic example is something like this. X e to the x. Let's stick a 2 there, just so that we can use some of the other rules, so that you can notice what's going on. So we've got these two pieces, so we should run through the list of things. We should just go first, can I just do that? Well, no. If it was just e to the 2x, I could do it. If it was just x, I could do it. But because they're multiplied together, it's too hard. Is it a chain rule sort of situation? No, because that would just be the e to the something. So I'm now down to saying the product rule is the next thing on the list, and so we'll say, look, it is two things multiplied together. That's what the product rule is for, and so I'm going to use the product rule. So we go x, we differentiate one of them, and keep the other, and then we keep the x and differentiate the other. So sometimes it's nice to put a plan in like that. So we differentiate the x, which would give me a 1, and we keep the e to the 2x, and then we keep the x and we differentiate the e to the 2x. So if it was just an x, it would give me e to the x, but it's not an x, it's a 2x, so I have to multiply by the derivative of the inside, and I'll get that. And so I'll get e to the 2x plus 2x e to the 2x. Because of course it's tradition to bring your plain numbers to the front of your term. And you can combine the product rule with the chain rule, which is what I did there. And there are times when you have to combine it the other way. What am I going to put there? Okay, really awful. Okay. This is awful, by the way. This is not pretty. But, it doesn't look too bad, and there are multiple ways of me dealing with this. So I will just show you one of them, but if you thought of a different way, it's okay to use that too. So one thing I can do is I can see this as x root x plus 1 all to the minus 1, because it's 1 over all of that. So 1 over anything is that thing to the minus 1. And I could see it as, x like that. Okay, so at this stage, I think it would actually be easier. So it's always easier to use the product rule outside the chain rule rather than the other way around. So I've got two options. I can say, oh look, if that was an x, I would know what to do. Differentiate that and times by the derivative of the inside. Or if I wanted, I could expand it out, because I know that powers come in over times. Like that. And when you do powers of powers, they multiply. And now I can just use the product rule as normal without having to do a product rule inside the derivative. So I'll differentiate this one and keep the other, and then I'll keep this one and differentiate the other. Okay, so differentiate the x to the minus 1, so minus 1 x to the minus 2, and keep the x plus 1 to the minus half, keep the x to the minus 1 and differentiate the minus a half, so that will be minus a half x plus 1. Now just a second, minus a half minus another 1 will be minus 1.5, so minus 3 on 2. And then because it's not just an x, I would have to multiply by the derivative of that, which is 1. And so I've got horror nope. So that minus a half can come out the front, which is awful. I don't like it, but it is an answer. Most people would traditionally get rid of their negative powers if they were doing this. So you would go, because both those powers are negative, It's tradition to not have negative powers, but it doesn't really matter. You could have left it as the previous one. It's just a little harder to read, that's all. Okay. One more. Yeah, that'll do. And then finally there's the quotient rule. Technically, the product rule and the chain rule are enough to figure out anything you could ever need to figure out. Okay, you don't technically need the quotient rule, but it does cut down a little bit of work. So you can get by without the quotient rule, but it is important to know that it's there so that you can understand other people's work. The quotient rule is designed for situations where there's a division. That's what quotient means. Something like that. And then when you differentiate it, you'll differentiate the top and keep the bottom. You'll subtract and you'll keep the top and differentiate the bottom. And you'll divide by whatever you had on the bottom squared. So you'll see the top bit is very similar to the product rule. It's just got a minus instead. And I would recommend, I often get it round the wrong way. It's really easy to get it round the wrong way. And one of the things that helps me remember is that I always differentiate the top first. That's what reminds me. So it's easy for me to remember that the bottom is squared. For some reason, it's easy for me to remember the bottom squared. And so I notice that the bottom isn't differentiated here. And so the first thing I write on the top, the bottom is also not differentiated. So when I begin this, I don't differentiate the bottom. When I begin this, I don't differentiate the bottom either. So that's one thing that I remember. I say I don't differentiate the bottom when I first start. Okay, I keep the bottom as it is when I begin this process. And it looks more difficult, and that's because it is. And you can get around this by doing the product and quotient rules, product and chain rules. But this is slightly shorter for some functions. Something like that is a classic quotient rule problem. And so we'll run through this. I've got to differentiate the top and keep the bottom. And keep the top and differentiate the bottom, and then square the bottom. Like that. So differentiate the top would be 1. Keep the bottom, keep the top and differentiate the bottom. And you'll find that when you do these things, often some things on the top cancel out. And this one's particularly pretty. But sometimes they won't, right? So if I had something like this, e to the x on x, so differentiate the top and keep the bottom, and now keep the top and differentiate the bottom and do the bottom squared. Which is awful, right? Things don't cancel. And it's just tradition, remember, to put powers at the end of an expression, so I could have left it as e to the x times x, but it looks prettier to have x e to the x. So there are all our rules for differentiation, except the final rule, which doesn't come until you do partial differentiation, which says that when you're doing partial differentiation, then what you need to do is you need to pretend that all the variables except whichever one you're differentiating with respect to are zero, are not changing. They don't count as variables, they only count as constants. So So for example, I might say that f is, x squared y minus y plus 3z x, something like that. And so if I want to differentiate that, I have to pick one of the variables to differentiate with respect to. So this is saying I'm going to differentiate with respect to x. So what I'm going to try and figure out here is when x changes by a little bit, how much does y change? Does f change? Okay? But technically I'm ignoring what happens when y and z change, so I'm going to presume that they don't change, which means I'm assuming that they're constants. And so it can help you to focus by actually underlining the things that actually count as variables. Everything else counts as a constant. So when I look at this, I go, okay, constants multiplied on will still be there after I differentiate. I know that rule. Constants multiplied on are still there after you differentiate, and y counts as a constant today. And the derivative of x squared is 2x. Constants added or subtracted will disappear when you differentiate, so that's gone. The next one is that the 3z is a constant and it's multiplied on, so it will still be there afterwards, and the derivative of the x is 1. Okay, so one of the reasons why I state that rule about constant multiples the way I do is that it helps me do partial differentiation. So I'm always saying, this is a constant and it's multiplied on, so it will still be multiplied on when I'm finished. And that helps me to focus when I'm doing partial differentiation and get the answer right. Note that this is also known as f sub x, right? I've got another choice as to what to call it. I could call it either df on dx or f with a little x at the bottom. They mean the same thing. Okay. And just to point out, something like that. So if I curly differentiate it, that means I'm wanting to know how f changes when x changes, but ignoring the fact that y might change. We're going to pretend that y doesn't change and therefore it's a constant. So let's have a look at this. I have two things that both have x's in them. I'm going to have to use the product rule. So I can go, the derivative of the x is 1, and I keep the e to the xy. And now I keep the x, and I differentiate the e to the xy. Now let's just look at that. If it was just e to the x, so I'm going to have to use the chain rule because I've got something other than just x in the power there. If it was just e to the x, the derivative would be e to the x. But it's not e to the x, it's e to the xy, so I have to multiply by the derivative of that. And let's see, y is a constant, so it'll still be there, and it's multiplied on, so it'll still be there when I differentiate, and the derivative of x is 1. And so I get e to the xy plus x, y, e to the xy. Whereas on the other hand, if I had done df on dy, let's look at df on dy. So since the dy is what I'm interested in, the x's count as constants, so let's have a look at this. That's a constant, excellent. So I don't have to use the product rule this time because it's a constant. Constants multiplied on will still be there after you differentiate. And then I can differentiate this. Now if it was just y, I would know what to do, and so I will keep it, if it was just a y, it would still be e to the y. It's not just a y, it's an xy, and so I have to multiply by the derivative of what's there, and the derivative of what's there, well let's see, x is a constant multiplied on, and so it's still there, and the derivative of y is 1. And so I get this. You really just basically have to practice partial differentiation a lot to get used to how it works. Okay, so it takes a lot of practice to not miss anything, and having some mantras to say to yourself like, it's a constant multiplied on, so it'll still be there, or I would know what to do if this was just x, but it's not x, so I'll do this. And that's how I always do the chain rule. It helps me focus. Okay, so they are your rules of differentiation, including partial differentiation. And the quotient rule is the hardest one in partial differentiation to really get a handle on. Doing partial differentiation with the quotient rule at the same time can be quite tricky. I might just do that, just in case your lecturer asks you to do that sort of thing. I'm pretty sure he doesn't, but you never know. Okay, that's a pretty good one. Maybe I'll put a 2y there. Okay, so if it was just a 2y on the bottom, I could have cancelled the y's and it would have been x on 2 and everything would have been happy. But it's not because of that plus. I'm going to have to use the quotient rule. So do df on dy. So let's see, that's a constant, that's a constant. And so I'm going to have to use the quotient rule. So I'm going to differentiate the top. Well, I'll do the bottom squared first because I know that's going to have to happen eventually. I'll differentiate the top. Now, x is a constant multiplied on, so it will still be there. And the y will differentiate to give a 1, so that's the derivative of the top. And I'll keep the bottom. And now I will keep the top and differentiate the bottom. 2 is a constant multiplied on, actually 2y will just give me a 2. The derivative of x is 0 because it's a constant, and so I'll just get that. So I have x, 2y plus x minus 2xy over 2y plus x squared. And just in case things cancel out, I will expand this out. X times 2y is 2xy. X times x is x squared. Aha, they did cancel out. You know how I said when you do the quotient rule, things often do? Well, there you go. So look at that. This is telling me that df on dy is always positive because they're both squared, by the way, which is one of the useful things to know in economics. That's saying if I change y, no matter how I change y, f will always go up, no matter what. All right, so that's sort of the rules of differentiation. And you'll find that sometimes you have to combine the rules together like I did there. I had to use my partial differentiation rules and my quotient rules simultaneously. And getting a handle on doing that, and sometimes coming up with problems where you're forced to do both is actually quite good for you, even if you don't get to the end of the problem. Right. So after all those rules, the next stage is, well, what can I do with derivatives? You know, what can I do with them? Well, what I can do with them is I can do all this useful stuff. Okay, so the first thing we can do with derivatives is that we can find the slopes of tangents. Okay, so we can find slopes of tangents. That's something that we can do with them. And so the idea is that if we think of our derivative of our function as a graph, then at any particular x, I can go up to the function and I can draw a line like this, and that's the tangent. And the slope is dy on dx. And the reason the slope is dy on dx is that if we go a little bit with the x's here, I know that a change like that of dx will force a matching change in y of dy, right? And I know that because I've oriented my y's upwards, I know that changes in y are up and down, and changes in x are left and right, and so I've got the slope of this line must be dy on dx. Okay? So there's this classic thing that they ask you to do is to interpret slopes. And you say, well, I found the slope of this function, and you go, well, I could interpret that as the rate of change of x with y. You know, when x changes by a bit, it's what y changes by. I can also interpret it as the slope of the tangent at that point. Okay, so that's something that you can do. And you do all this awesome problem solving where you can go, you know, what's the equation of the tangent at that point? Have you been asked those ones? Doesn't sound familiar. Okay, that's cool. You know all this stuff where you can figure out what the equation of that blue line is based on the slope, and you can go the y equals mx plus c thing. And so you can find slopes of tangents. Okay. And connected to finding slopes of tangents is finding maximums and minimums. Maxima and minima. So maxima is the plural of maximum because it's Greek. I think Greek, anyway. I think it's Greek. Interestingly, in Hebrew, plurals often end in whereas in Greek, singulars often end in That's why they have cherubim.
You mean Latin?
Sorry?
I think you mean Latin.
Latin? This one Latin? Yeah. But I know in Hebrew, though, plurals end in because you have cherub and cherubim. Yes. But yeah, it sounds maximum. Yeah, that sounds Latin, doesn't it? I get a bit because one of the worst things about maths and science is that sometimes we make words out of both Latin and Greek simultaneously. Dinosaur names tend to be like that. They're half Latin and half Greek. So, yeah, awful. Anyway, so we can find maxima and minima, and the concept behind it is that at a maximum or a minimum, the slope of that tangent will be 0. So, oh look, slope is 0, slope is 0, slope is 0, slope is 0. So the concept, the idea is, the process is that to find a maximum or a minimum, you need to find them all, and you find all the places where the derivative is 0. So this is your process. So your process is you go, number 1, find f dash x as a formula. 2, write your equation f dash x equals 0. 3, solve to find your x's. You know, there might be, you know, various different things. And then your last step is to sub them all back into the original function to figure out which one actually is the highest. Oh, you're supposed to do the second derivative to see if they really are maximums and minimums, you know. So there's a thing called a sign diagram. Do you do that in this course? Or do you just do second derivatives? Second derivatives, okay. Technically, they're local maxima and minima, because to say something's a local minimum it's actually very good on my picture here. You can see, looking at this function, I would think this was a minimum. It actually is the minimum. I think this is a minimum, but if I zoom out a bit, I can see the whole function. I can actually see it really is a minimum. But if all I was looking at was this bit here, from that information I would think it was a minimum, but it's not the minimum of the whole function. The minimum of the whole function is here. So it's just a minimum locally. It's lower than the points that are near it on the graph. Okay, so that's my process. I've got these 5 steps, possibly more depending on how you say it, and it's best to do it with an example. Oh, I'm not going to do that. Maybe I will. Just need to set it up right. Yes, okay. Okay, so step one is I find the derivative. Like that. Oh, that's a 4. Sorry about that. I'll have to find the second derivative, and I'll do that later. Step number 2, I'll write my 5x to the 4 minus 6x squared equals 0, and then I'll solve it. So, solve. So most of these things you've got to factorise. I could go 5x to the 4 equals 6x squared, but that's not the best approach. They both have an x squared in them, so I'll pull that out. And I'll get that. And so I either get that x squared equals 0 or 5x squared minus 6 equals 0. So once you've got two things that are multiplied together that give the answer 0, this only works if the answer is 0, you make them both equal to 0 separately. This one tells me that x is 0. This one tells me that 5x squared equals 6, which is telling me that x squared is 6 on 5, which is telling me that x is whatever. Wow, look at that. Plus or minus root 6 on 5. So x equals 0, minus root 6 on 5, and plus root 6 on 5. They're my three, what they call critical points. And I can't tell yet whether they're local maxima or local minima, or possibly I might not be able to tell. So I'll just find f double dashed x. I'll go back to f dashed, which was 5x to the 4 minus 6x squared. So I'll have 5 still there, 4x cubed minus 6 is still there, 2x. So I've got 20x cubed minus 12x. So finally I'm going to have to sub that in. So if x is 0, f double dashed of 0 is and I can't tell, right? Because this doesn't tell me anything. The second derivative being 0 tells you nothing about that point. Now I was always taught at this stage to just figure out what the function value is nearby to both sides of it, just to check, or to look at the slopes. So that's what I was taught to do. So I'm just going to do that at this stage. So here's 0, a little bit less than 0, f dashed x. So if x is less than 0, f dashed x, which was 5x to the 4 minus 6x squared. So if x is a really tiny negative number, I'm going to get a negative answer there. So I can pick like minus 1, for example. I just need to make sure I pick something that's not beyond the other thing, and minus 1 will actually do the trick. So f dashed of minus 1 is minus 1 to the 4, minus 1 squared, which is 5 minus 6, which is negative. And x is greater than 0, I'll choose f dashed of plus 1. Which is still negative. So yeah, it's not a local maximum or a local minimum. It would only be if the sign changed from minus to plus or plus to minus. So since same sign, it's neither nor minimum. If it was, if this was plus and this was minus, or the other way around, you could tell if this was minus, it's coming down here, and if it was plus, it's going up there, and that would make it a local minimum, but if it was the other way around, it would be a local maximum. So, all right, so that was x equals 0. When x equals minus root 6 on 5, f double dashed x is 20 lots of minus root 6 on 5 cubed minus 12 lots of minus root 6 on 5, which I have no clue whether that's positive or negative. Root 6 on 5 is sort of 1-ish, so it's got a sort of minus 1-ish plus 12, it's going to be negative. Which makes sense, it's coming down, yes. Which is negative, so it's a local max. Yep. And when x equals plus 6 on root 6 on 5, it's going to be positive. So it's a local min. So positive means it's curving generally upwards. I believe that your lecturer would call that concave. And negative means it's generally curving downwards, which means it's what your lecturer would call that convex. In the School of Maths, they don't have convex as a word. It's just called concave up and concave down, which is easier for me because it's up and down, but you have to remember that which one is concave and which one's convex. I remember convex is that it's like, I know that when you've got from science, when you have a bubble of water, a drop of water sitting on a table, it's called a convex surface, and the curve is pointing downwards. So that's how I remember it. Yeah. Okay. And we can even find local maximums and minimums subject to, well, let me just do. We can find with partial derivatives. And in this case, the picture's not nearly so nice, though you can draw these awesome 3D pictures, and I forgot to bring one of them with me. In the Maths Learning Centre, there's a big model made out of paper mache. It's yellow and orange. If you're ever in there, ask to look at it, because it has a local max, a global max, a local min, a global min, and a saddle point. So it's a really awesome picture, but I can't fit it under the document camera anyway. So, and you can do this no matter how many variables you have. So it's really common to do it with only 2 variable functions, but 3 variable, 4 variable functions. And the concept is the same. So the idea is that back in ordinary functions, you know that the maximum is where the slope is 0, but it's also, you know that at the maximum, if you change it by a little bit, then no matter which way you go, it'll go down. Okay? So at the maximum, with ordinary functions, well, with any function here, you know at a local maximum of any function at all, you know that here at the maximum, if I go this way or this way or this way or this way, then my function will go down because I'm at the maximum. All the points nearby are lower down. So no matter which direction I pick, it will decrease in that direction. And at this exact spot here, I know that coming from any direction I like, if I come up here and then leave, I'll be coming up, going towards, and going down, going away. So at that exact spot, no matter which direction I come from, it should be flat. Okay? At that exact spot, it should be a slope of 0 at that spot. So the rate of change of x with respect to y at that exact moment should be 0. And so at any local maximum, at a local max or minimum, we know that df on dx will be 0, and df on dy will be 0, and df on dz will be 0, and however many of them there are, they'll all be 0 simultaneously. Okay? Because each of them is the rate of change of f from a different direction. And even if you don't think about it in different directions, it doesn't matter which of those variables you change. Nearby to that point, if you're going towards it and you change a bit, it should go up. If you're going away from it and you change a bit, it should go down, which means that if you just go past it, it shouldn't change overall. It should be roughly the same. Okay, so no matter how many variables there are, if you differentiate with respect to all of them and go create all of those equations and set them all to 0 and try and solve them simultaneously, then you will find a maximum or minimum, and you have this horrifying situation that sometimes it's a saddle point, which means it's a minimum in one direction and a maximum in another. And so it is possible, you know, can also get a saddle point where one of, you know, some direction, possibly not those ones, but some direction is the slope is negative, the curvature is negative, and some directions the curvatures are positive. Okay, so your procedure for 2D at least. One is find all the partial derivatives. Find all the formulas for your partial derivatives, and you set them all equal to 0, which will give you a set of equations, and then you have to solve them simultaneous. Okay, and that finds you the x's and the y's where the maximums and minimums can possibly be. And it's the combinations of x and y, or x and y and z, or whatever that you're interested in. And then number 4 is you're going to have to find your second derivatives. And number 5, you're going to have to sub in each of your x-y combinations into that, and it will tell you whether there's a whether it's a maximum, minimum, or saddle point, and sometimes it won't tell you anything at all. So sub x, y's into these to tell saddle point. So instead of coming up with an example off the top of my head, which is dangerous because it might not work, now, before I do that, I am just going to write down the actual rule. So from your notes, you know that if it is all based on the value of this. Those second derivatives put into this formula, it's a determinant. Okay, so if this comes out to be negative, then it's a saddle point. Don't have to do anything else. If this comes out to be positive, to be 0, then you just the test is inconclusive and we have no idea. Okay, so your lecturer will arrange that not to happen usually. And if this comes out to be positive, there's still 2 more things to figure out. If either one of fx or fy is positive, then it'll be a local minimum, like fyy positive gives you a local min, and if fxx or fyy is negative, it'll be a local max. If you've already found that this is positive, you will not get the situation where one of them is positive and the other one's negative, because that's covered by that one. Okay? So, and you will also not get the situation where they're both 0, because that's covered by that one. And so the point is that fxx and fyy, it is possible for one of them to be 0. As long as the other one's positive, it'll be okay. They'll either both be positive or one of them will be positive and the other one will be 0. So that's my rules, and I'm going to take the example from the notes. Okay, so my step 1, the first derivative with respect to x, so that would be 3x squared minus 3. Now y squared counts as a constant and it's multiplied on, so it'll still be there, and the x differentiates to give me a 1. And fy, let's see, that doesn't involve y, so it's a constant, so it disappears. That's a constant, so it disappears. X is a constant multiplied on, so it'll still be there. The derivative of 2y, y squared would be 2y, so we get 2x. 2xy. So that's step 1. We're going to set them all to 0. 3x squared minus 3 plus y squared is 0, and 2xy is 0. And then somehow we have to figure out what to do with this, okay? So usually one of them should allow you to figure out, so you've got two choices. Either you're going to rearrange one to get y equals in terms of x and sub that into the other one, or you're going to get solutions for x and y straight up from one of them. And so with this one we know that the only way to get this to be 0 would be for either x to be 0 or y to be 0. So we can go from this one, we can get that x is 0 or y is 0. And then we'll take those two options and sub them back into there. So I'll call this equation 1 and this equation 2. Sub into equation 1. So if x is 0, I've got that 3 times 0 squared minus 3 plus y squared is 0. So y squared is 3. So y is plus or minus 3, root 3. And if y is 0, I've got 3x squared minus 3 plus 0 squared is 0. So 3x squared equals 3. So x squared equals 1. So x equals plus or minus 1. It can sometimes happen that the total options you get in one of them are covered by the other. So what we need to do is we need to combine all these x-y combinations. So my critical points are my xy. So this one, the x is 0, and we've got a y of plus root 3. We've also got x is 0 and y is minus root 3. This one, we've got y is 0 and the x is plus 1, and also y is 0 and x is minus 1. So I get these 4 places where both derivatives are 0 simultaneously. So one thing to remember is if at any point you actually locate a particular value of one of them, when you find the solution, remember to do that one first. So I went, I was told x is 0, so both of these have x is 0. So that was step 3, right? Okay. My step 4 was find the second derivative. Okay, so fxx means I first differentiate with respect to x and then I differentiate with respect to x again. So I go back to my previous formula for fx and I differentiate it with respect to x. So let's see. That the 3 is a constant, and I'll get 2x. That'll disappear. That's a constant, so it disappears, so I just get 6x. fxy, if I differentiate with respect to y, that doesn't have a y, so it's a constant, so it disappears. That's a constant, it disappears. That'll give me 2y. And then just to check, fyx should come out to the same answer. So I get this. Just to check that you've done everything right, you should do them both. You don't need to, but it's just worth checking. So this one says that I take fy, which is what this bit is, and then I differentiate with respect to x. So this time the 2 and the y are constants, so they will still be there, and the derivative of x is 1. Yep, so that's good, it's working properly. They both come out to the same answer. fyy, I take this, I differentiate with respect to y, so the 2 and the x are constant, so they'll still be there. Derivative of y is 1. Okay, so 2x. Okay, so I've found my second derivatives, and I sub in to help me figure out what. So let's sub in my points. So I've got the point xy equals 0 root 3. So fx was 6x, which is 6 times 0, which is 0, so xx. fxy was 2 times y, which is 2 root 3. fyy was 2x, which is 0 as well. And so I've got that fxx fyy minus fxy squared. fxx is 0, fyy is 0, fxy is 2 root 3 squared, but that's negative, so it's a saddle point. So at that point I have a minimum in one direction and a maximum in the other. xy equals 0 minus root 3. fxx is 6 times the x, which gives me 0. fxy is 2 times minus root 3, so minus 2 root 3. fyy is 2 times the x, which is 0. So fxx fyy minus fxy squared is 0 times 0 minus 2 root 3 squared, which is still negative. So you have another saddle point. xy is 1, 0. So fxx is 6 times 1, which is 0, which is not 0, which is 6. Easy to fix. fxy is 2y, and y is 0, so that's 0. fyy is 2 times 1, which is 2. And so therefore fxx fyy minus fxy squared is 6 times 2 minus 0 squared, which is 12, which is positive, and so therefore it's a local minimum. Technically I should just go back and go, well, I got a positive answer, and I go back here and both of them are positive, so it's a local minimum. Okay, and fxx is positive as well, and so therefore it's a local minimum. xy is minus 1, 0. fxx is 6 times minus 1, which is minus 6. fxy is 2 times 0, which is 0. fyy is 2 times minus 1, which is minus 2. fxx fyy minus fxy squared is minus 6 times minus 2 minus 0 squared, which is plus 12, which is positive, and fxx is negative, so therefore it's a local max. So this particular function had a local minimum, a local maximum, and 2 saddle points. So because it has saddle points, that generally means it doesn't actually have a global maximum. Yeah. Okay, doing really well. Been talking for quite some time now, getting very tired, but I have one more thing which was specifically asked for, which is the thing that most people find hardest, which is Lagrange multipliers. And that's a specific method of doing this, of trying to find maximums and minimums. So at the moment we've been able to find a local maximum and a local minimum. That's what we're aiming for. It would, if it was possible to find a maximum at all, it would be at one of those places. But the question is usually not that you just want to find the local maximum minimum of a particular function. you actually want to find them of a particular function subject to some sort of constraint. And so you don't just have your original function, you have some other function that you have to come out to a particular answer. What page am I up to? That was page 19. That was page 20. Okay, so I'll sharpen my pencil while I collect my thoughts about this. I'm going to do an example that only has an ordinary function so that you can see how it's done. And then I'll do one with a multivariable function. So the purpose of Lagrange multipliers is to find a maximum or a minimum. Okay, it's similar to the whole for doing derivatives and setting them equal to 0, and we still do that process. Okay, so we can find maximum or minimum subject to constraints, which means we're going to do Lagrange multipliers. Now Lagrange was a very clever person because he discovered that if I want to solve a problem that's basically a two-dimensional problem, but I have a constraint, he managed to do it by saying, well, why don't we make it a three-dimensional problem and it'll be easier. Now normally three-dimensional problems are harder than two-dimensional problems, but possible is easier than impossible. So that's why it works. Very clever. So the concept is that what you normally do is that you take your original function and you create a brand new function which is related to your original by adding on this bit with the Lagrange multiplier. So I'll do it with that one variable first, but this is your process. Next year, you'll do it with, if you do the intermediate math Econ 2, you'll do this with multiple constraints simultaneously. Okay, but that's why they save that for later, right? But I'm just warning you now. So the process goes like this, and even for those processes, it's not significantly harder. It's just longer. It's not harder. It just takes longer. So your process goes like this. You create a new function. Which your lecturer calls G. So this is your original function plus lambda times constraint. Note that some lecturers do it as minus lambda times constraint, and sometimes the constraint is written one way or the other. Doesn't much matter. You should be able to figure out everything that you need from this. Okay. And the basic idea of it is this is a new function and now it has one more variable than it used to. And the reason why this works is to do with that picture I was drawing. You're saying that you want your original function to be at its maximum, so you need its derivatives to be 0. Okay, which is you know has to happen. You know that the derivatives of your original function have to be 0 in order to satisfy the constraint. But you also know that suppose you're at the constraint and you moved a little bit one way or the other, you don't actually want, so suppose you want something to come out to 5 in this constraint. You don't want to move away from it being 5. Okay, so you want to simultaneously want this, the derivative with this to be 0, and you want that constraint to be 5. So you know that if you want to move a little bit away from 5, you don't want it to actually, a little bit away from the x's and y's that you've got, you want to still maintain it at 5. So what this lambda is a measure of how far away from the constraint we are, in a sense, sort of. Anyway, we create this new function, and we're going to treat this as a brand new function. It's got 3 variables now. We're going to do the exact same thing that we always do, which is do all the derivatives equal to 0 and solve them simultaneously. We're not going to do saddle points this time because we don't care. We're just going to run with it. Okay? So we create a new function, do the derivatives, gg on dx, dg on dy, dg on d lambda, because we've got an extra variable. Set them all to be equal to 0. And solve them simultaneously. What I'm not going to do at the final step is do the check with the second derivative test. Okay, that's not included here. Okay, but there's a key point with this solve simultaneously. You want the lambda to go away. You don't actually care what lambda is, because you only added lambda in order to help you solve the problem. It wasn't part of the original issue that you were trying to solve. It's the x's and the y's, or the l's and the k's, or whatever it is that you've got that you're actually trying to find. You don't care what the lambda is. Okay? So you need to eliminate lambda. That's your actual goal. You do need to try and figure out what the x's and the y's are and what combinations work, but you're really hoping to eliminate the lambda. Give me a second. Okay, I'm just going to do this. It's going to sound stupid, but I want to do it for a one variable function, okay? Okay, let's maximize f of x as x squared, subject to 3x minus 1 equals 7. Now, we don't have to use Lagrange multipliers for this. That's not necessary, but I just want to show you how it works. Because what we should do is we should actually figure out that x is in, let me not pick 7 if you don't mind, I'm going to do 5 if that's okay. What we should do is we should go, well, 3x minus 1 equals 5, and solve that and figure out that actually x has to be 2, and we'd sub the 2 in and we'll get 4 as the answer. Okay, so that's what we should do, but I just want to show you that it's going to work anyway. So it's my original function plus lambda which is that. So that's the traditional way of dealing with it. We take this function and we go answer minus the function. Okay, and then we differentiate. We've created our function. We do our derivatives. So dg on dx is 2x from here. Now this one, that lambda counts as a constant, and so it will still be there when I differentiate because it's multiplied on. And the derivative of 5 is 0. The minus will still be there, and the derivative of 3x minus 1 is 3. Okay, so I get that. So I've got my 2x minus 3 lambda, and I've also got my dg on d lambda, and so I've got, let's see, x squared goes away, it doesn't involve lambda. This is a constant, so it will still be there when I differentiate. And the lambda will become a 1. Okay. Okay. So the aim is to figure out what x is, and so we try and make the lambda go away. And so we go, set them equal to 0. And all well and good, my lambda is actually going to come out to be whatever it is. And I solve them simultaneously and it tells me what the lambda is, okay? So I can go 2x minus 3 lambda. So from the second one, I've got that 6 equals 3x, and so 2 equals x. And then I can sub that into the other one, 2x minus 3 times 2 equals 0. Oh, there's no solution. Crap. Let's ignore all of that, because I thought it would be fabulous and work out the way it is. Oh, that's okay. I subbed into the wrong one. 3 lambda, it's 2 times 2. So I've got that 4 3 lambda, so lambda is 4/3. So what this tells me is that x equals 2. Okay, I ignore the lambda. My main point was that it is okay that you don't use the lambda at any point. Okay, it is okay that the value of lambda that you find doesn't come into your final solution. Now this is not the best way of solving the problem that I just had. Okay, I just wanted to illustrate that it works even in one-dimensional functions, and there are some situations where that might actually be useful. But let's do a proper one. And it works for any number of constraints. You just put more lambdas in, you know, lambda and mu and nu and rho. Okay, so here we go. Let's do this one. F of xy is x squared plus y. That's not to the power of x, that's just y times x. Subject to x plus 3y equals 5. Okay, so we're going to do the same trick. I'm going to go step number 1, we'll create our Lagrangian. It technically has 3 variables. I take my original function and I add my lambda So your lecturer, you always take the plain number, subtract the other bit in this bit here. It shouldn't matter even if you do it differently, even if you subtract it the other way around, it shouldn't matter. It's just that your lambda will come out to be negative, and so you'll get more chance of losing minuses, that's all. So I'm going to calculate my derivatives. So let's do dg on dx. Okay, so that doesn't involve a y, I don't have to worry about that, that's just 2x. The y is a constant multiplied on, so it'll still be there. The derivative of x is 1. The lambda is a constant multiplied on, so it will still be there. The derivative of 5 is 0. The minus will still be there. The derivative of x is 1. The derivative of that doesn't count because that's a 0, so we get this. 2x plus y minus lambda. Okay? And the other derivative, dg on dy. Okay, so this time we differentiate this with respect to y. That doesn't have any y, so it goes away. The x is a constant multiplied on, and the derivative of y is 1. The lambda is a constant multiplied on. The derivative of 5 is 0. The minus will still be there. And the derivative of x is 0 with respect to y, and that will leave me with a 3. So I get x minus 3 lambda. And then there's technically dg on d lambda, which, let's have a look at this. These don't involve lambda, so they go away. That's a constant multiplied by lambda, so what's left is my 5 minus x plus 3y. So we'll set them all to 0. So I've got the 2x plus y minus lambda equals 0, and x minus 3 lambda equals 0, and 5 minus x plus 3y equals 0, and I have to solve these simultaneously. So normally what you do is you figure out the lambda first and try and make everything happy based on that. There are multiple ways of dealing with that. One way would be to multiply this equation by 3 and subtract the two of them. One way is to figure out what lambda is in terms of the others. One way is to set them all equal to lambda and divide, which looks like that's your lecturer's preferred approach. When I see this, I don't see division as the best plan, but there are many different approaches to take at this stage. I personally would go from number 2, x equals 3 lambda, which means that lambda is x on 3, sub into number 1, 2x plus y minus x on 3 is 0. And I just times everything by 3 to get rid of that x on 3. So we've now got 5x plus 3y equals 0. And from 3, I had that x plus 3y is actually 5, because that was my original constraint anyway. And so if I subtract those two equations, I should get just the x now. So 5x minus x is 4x, 3y minus 3y is 0, so x is minus 5 on 4. And then I just try and figure out what y is. So usually you sub it into the equation, like this equation here. I'll call that equation 4. So I've got that minus 5 quarters plus 3y equals 5. Just times everything by 4 because I don't like those fractions. So in fact, xy has to be, x was minus 5 on 4 and y was 25 on 12. Now technically I don't actually know whether that gives me a maximum or a minimum. I should probably sub in some values of x and y nearby to that into the original function to see if it really is a maximum or a minimum. Because it could be either. I don't know which one it is. So I should just go back. Technically, I think the value of lambda tells you whether it's a maximum or a minimum, but I should just go back and sub in something nearby to that, or any other point at all, because sub in this point, and if I sub in any other point at all, if it's higher, then this must be a minimum, and if the other point's lower, then this must be a maximum. So I could say like g of, no, the original function was f, wasn't it? What was my original function called? X squared plus y times x no clue really. I'd have to ask a calculator that one off the top of my head. 120, no. Someone could calculate that, that'd be great. That doesn't matter really. If I pick any other point, is that positive or negative?
Negative.
Okay. If I pick any other point that actually satisfies the constraint, so if I go back to my constraint, I've got x plus 3y is 5. So I could put x is 5 and y is 0, and that satisfies the constraint. So pick. And see what I get with that. So what was this answer? Negative what?
25 over 25 divided by
24.
Yeah.
Cool. And so this is bigger than that, and so that must be a minimum. Because any other thing is that I pick some other point that satisfies the constraint, and its value is higher, and so therefore this must be a minimum because it's lower. So since gives a minimum. And there in fact must be no maximum therefore. So I didn't maximize it, I minimized it. Oh well. I tried to maximize it, but in fact there is no maximum, it's a minimum. So I'll just go back and change the original question, shall I? If only you could do that in an exam, right? My answer's different, I'll just change the question. Your lecturer will have been very careful to make sure it will work. So I'm not sure he expects you to check it at all. I should point out that a different preferred method is to figure out what the lambdas are equal to and equate them. So just note, alternative method. Back when I had my lambdas, just here, back when I had my three equations, I could have done, from 1, I get that lambda equals 2x plus y, and from 2, I get that lambda equals x on 3. And then since these both things are both equal to lambda, I can say therefore 2x plus y equals x on 3 and solve it from there. And then combine with the x plus 3y equals 5. Okay? So there's a traditional method that says figure out what lambda is, set the lambdas equal to each other, and go for it. But that particular approach will only work if you've got 2 variables to begin with. If you've got 3 variables to begin with, there might be 3 possible answers for lambda and it's going to get messy. So you're not in that situation, but just warning you that in the future it might not be the best plan to make lambda equals. Yeah, but in some situations where you don't have any variables and it's all just letters, that's the only thing you can do. All right, do you have any questions? Anything you want me to cover before I run and fall in a heap because I'm really tired? Cool. I am happy to keep going. I have to go to the drop-in centre pretty much straight away anyway. Yes, so do be aware that you can visit the Maths Learning Centre for anything mathematical, be it this or stats or anything like that. So I know Business and Economic Stats is on, what, Wednesday? Thursday? I don't know. Are any of you doing Business and Economic Stats? What day is that on? Wednesday. So I won't be here tomorrow because I'll be at Roseworthy because they have a stats exam on Wednesday as well. But the other staff will be able to help with Bess if you want to talk to them too. But of course, but this exam's Saturday. Okay, so we're open until the end of the week. We'll only be around in the morning on Friday because we're not officially open that day. But if you do want to come and chat to us and nobody's there, there's a phone number on the wall. Call that and we'll hopefully be able to answer. Okay. Cool.